In this lecture, we are going to talk about matrix operations and properties. So there are some specific types of matrices, some definitions, and some operations that we frequently use when we deal with matrices. So let's start with diagonal matrices. A diagonal matrix is a matrix where all non-diagonal elements are 0. Usually we represent this matrix as D is equal to diag D1, D sub 2, and D sub n. So what does that mean? That means Dij is equal to Di if I is equal to j, and 0 if I is not equal to j. So a specific case or example of diagonal matrices is identity matrix. Identity matrix, which is represented by I, is in R n by n, is a square matrix. A square matrix means it's n by n with ones on the diagonal and zeros everywhere else. Right, if you want to show identity matrix as a diagonal matrix, it's I is equal to diag 1, 1, and 1. So what's the property of this identity matrix? For all A in R n by n, A multiplied by identity matrix is equal to A is equal to I multiplied by A. Something that we should note here, so A is n by n. When we say A multiplied by I is equal to A multiplied by I sub A, so dimension of I is determined based on where it's located. So this is n by n. So in this case, I is n by n. In this case, this is m by n. So I should be m by m, so that these matrix multiplications can be performed. They should be feasible dimension-wise. So usually we don't write the dimension of I. We don't say I n by n, but based on the context, wherever I is, its dimension is determined based on the matrix, which is after that or before that. All right. The next definition is transpose. The transpose of a matrix results from flipping the rows and columns. So, for example, given a matrix like A, which is m by n, its transpose, which is written as A transpose. As you can see, the dimension now it's n by n. So it was m by n, now it's n by n. Is the n by m matrix whose entries R. So A transpose IJ is equal to AJI. Gives you each element of A transpose. So there are some features for A transpose. There are some properties that we are going to discuss. Properties of A transpose. The first property, A transpose. Transpose is equal to A. The second property, if you have matrices A and B multiplied and then transpose, it's equal to B transpose A transpose. And the third property, A plus B transpose is equal to A transpose plus B transpose. Let's take a look at examples for this. Matrix A is 1, 2, minus 2, 0. So A transpose is 1, 2, minus 2, 0. A transpose is 1, 2, minus 2, 0, which is equal to A. You can find examples for other scenarios as well. The next definition is symmetric matrices. The square matrix, such as A, which is n by n, is defined to be symmetric if A is equal to A transpose. So in order to be symmetric, A should be equal to A transpose. And also, this matrix is anti-symmetric if A is equal to minus A transpose. All right, so for any given matrix A, for any matrix A, matrix A plus A transpose is always symmetric. So let's try to prove this. Proof. Let's call B equal to A plus A transpose. Then B transpose is A plus A transpose, which is A transpose plus A transpose transpose. But we already know that A transpose transpose is equal to A. So it's A transpose plus A. We can just change the location, A plus A transpose. So what's this? This is equal to our original B. So B transpose is equal to B. So this matrix is always symmetric. Also, what we can show is A minus A transpose is always anti-symmetric. Let's try to show this. I'm going to define matrix B to be A minus A transpose. So B transpose is equal to A minus A transpose transpose, which is equal to A transpose minus A transpose transpose. This one is A, so A transpose minus A. All right, what's this? This is equal to minus A transpose. So here we have our original B. So this is minus B. So B transpose is equal to minus B, which is definition of anti-symmetric matrix. All right. So what's the use of finding a symmetric and anti-symmetric matrix from A? Now we can say for all square matrix A, which is n by n, we can represent this matrix represent this matrix as a sum of a symmetric and an anti-symmetric matrix. How do we do that? A is equal to 1 over 2 A plus A transpose plus 1 over 2 A minus A transpose. So as you can see, the first part, this is a symmetric matrix. This is anti-symmetric. All right, the next operation that we're going to talk about is the trace. Trace again is defined for square matrices. The trace of a square matrix like A, which is n by n, denoted by trace of A is the sum of all diagonal elements in the matrix. In other words, trace of A is equal to sigma I from 1 to n, A sub ii. All right, so there are some properties for trace. Properties of trace. One, for matrix A, which is n by n, trace of A is equal to trace of A transpose. Second property, for matrices A and B, which are both n by n, trace of A plus B is equal to trace of A plus trace of B. Third property, again, for A, which is n by n, and T, which is a real scalar, trace of T multiplied by A is T multiplied by trace of A. Next feature, for A and B, where AB is a square matrix, trace of A multiplied by B is equal to trace of B multiplied by A. And again, for A, B, and C, where A, B, C is a square matrix, trace of ABC is equal to trace of BCA is equal to, let me write it here. Trace of ABC is equal to trace of BCA is equal to trace of CAB. And this can be expanded to more matrices. As long as the product of some matrices is a square matrix, you can change the location and still claim that the trace is equal in all scenarios. So the last property, I just want to show it for the scenario where we have two matrices, right? Let's say you have matrix A, which is in R n by n, and matrix B, which is in R n by n. So A multiplied by B is a matrix which is, let's say, C n by n. Now we are going to try to see what's going on. We have trace of AB, which is equal to sigma AB AB sub I from 1 to m, which is equal to sigma I from 1 to m. Now we are going to expand AB. Sigma j from 1 to n, Aij, Bji. All right. So now we are going to again like get rid of this parenthesis. So we have sigma I from 1 to m, sigma j from 1 to n, Aij, Bji is equal to sigma j from 1 to n, sigma I from 1 to m, Bji, Aij. So what we did basically, we just changed the location of this. So nothing has changed so far. Now, another thing that we did, we changed the location of these summations. All right. So in the next step, we are going to try to extract BA JJ from this. It's going to be sigma j from 1 to n BA JJ, which is nothing but trace of BA. So we started from trace of AB, and we showed that it's equal to trace of BA. So the last thing that we are going to talk about in this lecture are norms. The norm of a vector X is informally a measure of length of the vector. So there are several definitions for norms. For example, we have a commonly used Euclidean or L2 norm. How do we define L2 norm for a vector like X is x1, x2, xn? So the Euclidean norm or norm 2, L2 norm is equal to the square root of sigma I from 1 to n, x sub I squared. It is called Euclidean or L2 norm. So other examples, L1 norm. L1 norm of vector x is equal to sigma I from 1 to x, x sub I. Absolute value of x sub I. So this is L2 norm, this is L1 norm. Also, we define L infinity norm as maximum value of absolute values of x sub I over I. So what does x infinity mean? The largest absolute value of all elements of xi. The next norm is, so before talking about the next norm, all of the norms that we discussed so far are examples of families of LP norms. So we can show LP norms for real numbers p greater than or equal to 1 as, so norm p of vector x is equal to sigma I from 1 to n xi to power p, absolute value of xi to power p to power 1 over p. All right, so we also can define some norms for matrices. So this is LP norm, LP norm for p greater than or equal to 1, p real. So norms can also be defined for matrices. Example, we have Frobenius norm. Frobenius norm for matrices. How do we define that? Let's say you have matrix A. The Frobenius norm is a square root of sigma I from 1 to m, sigma j from 1 to n, a sub ij squared, which can be also shown as trace of A transpose A. So there are many other norms. When we move forward, if we need to define new norms, I'm going to discuss about them. But at this point, this is all you need to know about norms for vectors and matrices. So in this lecture, we talked about some more definitions and operations in matrix, in the matrix environment. First, we discussed diagonal matrices. Then we talked about identity matrix as an example of diagonal matrices. We defined transpose of a matrix. We defined trace of a matrix. We talked about symmetric and anti-symmetric matrices. And finally, we discussed about norms.